All right, trying out something new here. I'm basically solving some problems, and it's taking me into the statistical thermodynamic stuff, so I have to sort of figure out what I'm doing here. And essentially, the first thing I'm trying to find here is I'm trying to get a partition function going, which is this particular thing right here. And so I have to add in different states. So I have two states. I'm going to add the two states, and it's going to give me some kind of energy. So I'm just going to do that. And let's sort of figure out all these things. I don't really know a lot about statistical thermodynamics, but let's go ahead and do that. So just plugging in some numbers here. Press 5. So I'm gonna sum up the i's from E, and I have this negative beta EI. Okay, and I have two states here, so I'm just gonna sum them up. We have two two different types of energies. Okay, so this one isn't too bad. It's literally just gonna be one plus the other. E to negative beta epsilon. So that's not it's not a very difficult problem. So the second problem is getting me a little bit confused here. What I have to do is compute this average energy thing. Well, once I find Z, there's a couple of different things I can find. There's like free energy, which is not what I'm looking for. There's entropy, internal energy, and heat capacity. But I'm looking for the mean internal energy. So it's like the average V. Okay. Well, let's find the integral that we need to solve this. Let's find that integral for E. We're looking for E, total energy. Integral for mean internal energy? So let's see what this is. Oh, that's right. Um, it actually is this. So that's interesting. U is the same thing as hmm, why is U the same as E? I guess we are just finding average internal energy, so we would use the U. I was assuming that. Um, so the average, so the mean is the same as expectation value. Is that right? So mean and expectation value and average is all the same word. Okay, so that's interesting. So we have some vocab that we kind of have to just keep in mind. They are asking for, if they're asking for like the mean or the average or the expectation value. These are all the same thing, and we can often represent that with like this type of notation, or even putting a bar on top of it. So there's like two different ways that we can actually denotate these vocab words: mean, average, and I don't know if there's any other symbol for average. So whatever. But yeah, so these are going to be the three things. So if we want to calculate the mean, we want to calculate the average. Well, why? Why do we just? This is not the average though. But hold on a second. So negative v ln z over dv is not the average u. It's just u. So how do we calculate average u? Okay, so yeah, this is the total energy. But how do we get? This is some really weird stuff. The problem is that the statistical mechanics and stuff, this is all very complicated. Like I'm just asking, okay, so this is the total internal energy. U equals this stuff. That's correct. But this isn't the average energy. Got to figure out how to make this an average. How do I get an average? But this expression already calculates the average because it represents the thermal average. What? Oh my God. So the strange, wow, this is expectation value. The mean internal energy is the expectation value of the energy, which is defined by. Phew, man, this is really hard. But yeah, I mean, they are definitely showing here that the expectation value of the energy, let's say we start with the partition function z here, then we take the derivative with respect to this thing here. In fact, I kind of want to do that so that we have an answer. Uh, take the derivative of ln z. Differentiate 0 respect to b, since it's and that equals u. Okay, so internal energy is the same as outer energy. Oh, this is crazy. What? Okay. Internal energy represents the total energy on average. Well, I guess, it's a little bit complicated. I'm not exactly sure 100% why, but it turns out that the energy average is the same as the internal energy here. Or in fact, the idea is that this calculation, taking this partial derivative, already accounts for the average. And I'm going to guess that it has something to do with this z right here. Let me just see. So you already account for average because it contains z. Yeah, so apparently z already gives us the probability of all the states. So we're just basically, we already have like an average essentially. And we're just gonna basically go with this idea that this internal energy here is already, yeah, okay, let's just double check here with the class notes and see if this is matching up with what we get. Progress is very slow sometimes when it comes to these things, as you can see. But that's why I try to take very careful notes, so that way the progress has been made and we can return. Right now, I have to look at some more proof that this is actually correct, because I don't really understand why that is the case there. So let's see what this says. Oh my god, this is so complicated. Particle energies, number of microstates, U single. So PV equals K and nothing too much. We have this probability function. Did I put the probability function anywhere? Oh yeah, there was a thing I wanted to do for this particular probability right here. How many combos can we have here? I know this is a little bit different, but it's actually about the same kind of stuff. So I just want to make sure that in this particular situation be 2 to the n combos because we have two states, and the two states are going to be heads and tails, and depending on the number of flips that we do, that's going to essentially be this exponent. So 2 to the power of n is kind of representative of this, the number of combinations. Literally that. So I just want to double check to make sure that I'm making the correct calculation. So the number of microstates, omega, is equal to the number of states to the power of um, what do we call it, n, I guess. So yes, that is correct. So that's what we have here. Okay. Okay. I can do this kind of thing. I could say that this value is actually equal to this stuff here. See, over here, or in this particular case, would be here or here. Or here, just equal to this. So that's why we want to know about all this stuff over here on the side that doesn't seem to have anything to do with what we're looking at here, but it certainly is. Because that's how we get this omega thing, is to understand the concept of microstates and how many times you're going to flip that coin just gives you the number of possible options now. Alright, so that's nice. We tied that in. That's nice. Alright, so I think we have to find the calculation. We just have to solve this thing here. But I did want to just double check. I know, it's crazy. What the heck is U? U? Okay, expected average energy. Oh shit, we're given this. We're actually given this. In our notes. But it's a different formula. See, it's slightly different than what I have here. It may. I'm just going to write down what we are given here. When it says U, expected slash average. I guess they wanted to use that notation. So apparently it's the sum of the states over the states, and we have EI, PI. Oh dear. Okay, what the hell is PI? Think we have to. I think we have to. Wait, we have to define that. I think it's up there. Yeah, okay, so that's just the regular probability. That's kind of the most important. That's probably one of the more important integrals. But I'm going to do it right here on the right side. So PI, and I'll just say probability. 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 I need a little bit more descriptive. Not, but whatever. 1 over Z. And then we just have E to the negative EI over K. It's the KBT thing. We have to sort of always deal with. Why don't we just put it in terms of this? It's funny how it's quite exactly the same thing there. I mean, yeah, kind of. I know it's weird, but let me explain. Let me explain. We're almost there. We're almost there. We're almost tying this together in a big knot. Okay, this is correct. 1 over Z e to the whatever is the probability, and Z is in fact the sum of all that. And the reason why is because we want. Okay, I think I see what's going on here. This is the probability at that particular state. Probability is state I. Probability at state I. At state I. Or really of state I, that particular state to show up is going to be equal to this thing, and you do that. And the idea is that we want the sum of all the probabilities that we have here to equal 1. That just gives us 100%, right? Because we want it to be there, so we're going to put that to be 100%. And in order for this to be correct, then we just put, we have to put a integral here, and then set it equal to 1. So that's why we get this. It's essentially just the interval that we're. Okay, so this all sort of wraps it all together. I mean, I know it's kind of confusing, but at least I kind of get this loop. So, all right. I will go ahead and actually put this more on this side here, or something like that. Entropy is equal to this. Probability is equal to that. Yeah, that's a little weird. Why is probability? Well, okay, no, that makes sense. The idea is that each microstate has an equal probability, one chance out of the total microstates. That makes sense. But I think I have to put I here as well, because that's the probability of state of any of these states to happen. Okay. It should really be like omega sub I, but whatever. Not a big deal. Anyway, so here's the partition. Here's that number. I think we have enough information here to actually solve this, or at least now I'm starting to kind to come to terms with this idea. Oh yeah, no, that's what we have to sort of continue here to determine what the heck this is. This is EIPI. And PI, we said, was this. Okay, so in fact, we can just do a quick substitution, plug that in. Just take this really, and put it over here, and then just take the sum. The I is still going to be here. Alright, pull the Z out, and then we'll put the EI inside, and we still have this E to the power right there. Right? That works. And then we're given the E solution. If you know Z, you can compute U. AT squared D1 How on earth are we getting this value? How on earth are we getting this value? That is, I think I know how we're getting that value actually. We're getting that value because, what value we're talking about? Okay, we're talking about this value. This can sometimes be represented like this. We're going to have KB T squared. And then we have DLN with T. It's not a B on the bottom. It's a T. Right. Now, why does this equal that? That's a good question. That is a question I can't really answer right now. I have a feeling. So this 1 over Z thing leads us towards this, maybe? No, no, this is really complicated. How do we get that? Hey, yeah. How we arrive at kt squared, blah, 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 take z, and then we have, oh my god, this is a mess. What the hell? We are. What the hell? This is so complicated. This is like blowing my mind right now. Like, there's even two crazy things. So this much is clear. Recognize that this, well, no, this portion by itself can be written, bust out that purple, this stuff right here, that stuff is the same thing as negative and partial over partial b of uh, the sum. So for some reason, we're able to like get rid of the EI and just take a partial instead. That gets us the same thing. It is really, really weird. So we can get rid of the EI thing and into the partial instead. You can replace the sum over the energy states, the partial derivative, with respect to temperature. What? Boy, this is crazy. What is going on? Um, partial with respect to temperature. Wait a minute. We're turning it into a partial and of dB instead. It's very clear that it's the partial dB here for some reason. Really, it's the same thing as T, I guess. The reason is because if we look up here, clearly dB equals the inverse dt. The original energy is this. C, blah, 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 everything's good. That directly sums over the energy levels EI. This is what we sort of had to pull out, transform into this. I mean, use all the other stuff. That directly sums over the energy levels EI, weighted by their probabilities. My God. Whoa. EI is tied to the exponent? Wait, hold on. Okay, hold on. The sum can be written as that. And this right here is Z. Oh my God. Ah, so that's literally this. Oh my God. What is happening? What is happening, dude? What are we doing here? This is so crazy. The EI here. Some of the EIs and all that stuff can be rewritten as a derivative of Z because this is tied to the exponent. You can see we have it also in the exponent there. I will use that clear. Maybe I'll turn it gray just because the idea is we're kind of analyzing this EI over here. What the heck is EI anyway? Like I'm just completely a little bit lost here on this EI situation. What the heck is EI? Why can we treat the sum as a partial? Why can we treat the sum as a partial? EI represents the energy of the microstate. Okay, yeah, well, that much makes sense actually. Let me go ahead and make this blue actually here for this energy thing. This freaking energy we have to understand this. This is the energy of the ith particle. So E of not the this should have just been a capital E. It would have made a little bit more sense, but this is the state energy. Energy for state value. Okay, that's what this EI stands for. And if so, it makes a little bit more sense if we kind of think of it like that. Energy for the state value times the probability of state value. Alright, now this expression makes more sense, see? Because now we're just taking the energy of each state, multiplying it by the probability. But I still don't see how we're able to turn this into a partial. EI is here. EI is here. I'm just checking to see what this is. Is what? Let's see. Comparison of the streams available. Uh, what? Stream hub is good. Primary and backup streams? What do you mean a backup stream? I have no idea. Backup stream. Look, I don't care too much. Let's go ahead and continue this. Alright, so partition function z sums all over the microstates the statistical weight of each state based on the energy. The sum is connected to the partition function. Okay, the sum is connected to partition function, which is just this. Yeah, okay. This, by the way, is z, just in case we let's do something like this. Yeah, no, this is fine. This is fine. This is fine. Just making sure that we have a 1 over z. Oh, no. Oh, no. What is a 1 over z? Oh, oh. Well, that would finally clear up why this is internal energy. Just this. But if we want to find the average internal energy, then let's also include 1 over z. So we have to divide this by z. And it's funny because this little term here is actually z. How can we do this? There's a negative sign right here. Let's do something like this. There. Good enough. Now we have this term. Now it makes sense why we have dz over db times this gives us the average, whereas this does not contain. If I think we had a little bit misunderstanding earlier. Internal energy U is not to be average yet. We need to divide it by z. Yeah, there we go. Now it's making sense a little bit. See, this was the total internal energy, like I was saying. It's not equal to the energy. Almost. You have to divide it by z. That's the number of microstates, and that would give you the average. Okay. Okay. Now, I still haven't really figured out how this partial connects. That's sort of a big question here, but at least everything else is starting to make more sense. I can essentially, I obviously can solve this at this point, kind of, but I'm still very confused. I like to get the theory down. What the heck is this partial doing here? Why are we able to take this and turn it into a partial? Alright, let's try to, let's try to take the partial. Let's try to take the partial. Put it up here. So we're going to take the partial, and forget about the sum. It's going to use there. We're going to take the partial here, just as an example. If we were to do that, we're just going to get this thing again. It's just e. So taking the derivative of e, we get e. Then we have to multiply this by the derivative of the exponent, which is negative b. And then we're going to apply the negative, so let's just call it a positive b at the end of it. Or sorry, not positive b, positive ER. That is the one that is going to remain as the constant. Okay, yeah, okay. So this is correct. This is definitely true. Oh, of course. There we go. That makes more sense. Oh my God. Oh my God. Oh my God. It's literally just because you're taking the partial of E. When you take the partial of E, you're left with this. And this is what we have here. So you can just put this in and then just put your sum in. So like kind of pull the sum out and work with it without the summing and then just put the sum back in at the end. Oh my goodness gracious. We finally did it. We finally figured out why this partial is here. Oh my God. So you can see how there's something crazy. Alright. Alright, now I can solve the problem that I was looking at. So we have u is really equal to, an average u is equal to this negative dz over db, and then we have to multiply by 1 over z. And we just want to double check to make sure this is correct. Yes. Yes, it is correct. It is correct. But what is all this? This? What? 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 Oh God. What is this now? I mean, all this made sense. This made sense. But now this. Wait, oh my God. Well, I oh my God, this is so intense. AT squared. Okay. How do we get KT squared? KT squared D over DT over DT. Hmm. Using the derivative of ln of z, we avoid explicitly computing the sum and normalization factor which is built into the derivative. Oh, we can avoid doing all this calculation. We don't have to do any of this calculation. We can jump straight to this result. Right, but how the heck are we getting KT squared? Let's start with z partition function. And that. Okay, so we want to express this u in terms of temperature instead of b. Okay, okay, okay. Let's take a derivative here with respect to t. If we do that, this becomes negative t squared. Okay, very nice. This is going to help us because over here, this essentially is telling us that we can take dt and essentially sub it in for this dB like that. Alrighty, there we go. And so now if we wanted to do some dB stuff over here, you just plug in dt, um, and yeah, yeah. See, this stuff is on the denominator, and the dB is also on the denominator, so it goes to the top. And this is negative. This is already negative, so we get positive. Okay, okay, okay. Now, now we understand everything. Yeah, we don't even have to really do too much here, but we can do is we can say that the u is equal to kb t squared. Um, uh, since we have to calculate by doing differentiation, we're gonna differentiate the ln of c by t. So d squared, we're gonna take the partial derivative of the ln of z and the partial of dt. And well, yeah, I think I just have to calculate this partial. The partial some calculations I just have to do on the side over here. We're taking the ln of 1 plus e to the negative e over kb. Honestly, I think I have a feeling because we already know z, and it should be pretty easy to take a partial. It's possible that it's possible that using dz db and then just divide. It's possible that using this might be slightly better. Essentially just this. I think this one is going to be a little bit of an easier partial to take than to do the dt in this particular scenario. I'm sure that this is a valid formula in other scenarios. Right now, I think it would be better if I took the ln of 1 e to the negative b e and then try to take a partial with respect to that b. Beta epsilon times partial of what's in here, negative e. Is this supposed to be negative? So that ends up being positive, and then we just have to divide this answer by c, so we get a square on the bottom. You know, I think we finally solved it. Kind of screwed up my paper here. So do this again. Z equals okay, so epsilon z is supposed to equal 2 u. U is equal to the negative partial with respect to beta of z, and then we're going to multiply that by 1 divided by z. So what we're really taking is the partial of ln, this result here, and when we do that, 1 over 1 plus b negative beta times negative epsilon into negative beta epsilon. Make this a present. Okay, perfect. One line. Not even two. Okay, fine. I needed one line on the second one I put the answer. But that's a very nice one. Okay. Honestly, I think we might have enough information here to continue solving the rest of it. What the hell is that? Let's see. Internal energy, heat capacity, entropy, this free energy stuff. Oh my god. What is going on? Oh shit. Wait. Oh no. Look, it just like erased a bunch of stuff on my screen. Crazy. I might have to cut the stream right here all of a sudden. I can't undo it. Wait, what? In there, bring the equal sign. Life is rough. Life is rough. And you that is equal to this. Well, um, I'm gonna continue on this stuff and see if there's any more info we need to gather. T, as t goes to 0, negative epsilon over kb 0, 1 plus 3 negative epsilon over kb 0 squared. Um, U equals all this. We're sending t to 0, and when we do that, oh my god, we get negative infinity, e to negative infinity. So, doesn't it just mean negative infinity? Doesn't it just go to 0? Yeah, I'm pretty sure that equals 0. An interpretation. Internal energy. What happens if the internal energy is 0? Uh, well, okay. I mean, things aren't moving. Okay. Let's do that for infinity now. We're just going to send this to infinity. Essentially, that turns into 0. So this becomes 1. This becomes 1. Oh, what? What the heck? That's kind of weird. Interpretation of this result. Thing is, I'm not really supposed to be telling you these answers, so these formulas here are just basic knowledge, but I can't really show you what I'm doing with it. Use the postulate of statistical mechanics to compute entropy. Entropy as a function of energy. Huh. X free energy. Free energy. No idea what that interpretation could possibly be. I'm not really worried about it. So Helmholtz free energy. This is Helmholtz free energy. Helmholtz. 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 Helmholtz free energy. Okay. The maximum amount of work that a system can perform at constant temperature and volume. Okay. Well, well. Alright, we have to deal with this. We have to deal with this Helmholtz free energy. Yes, we gotta calculate entropy and I'm gonna put this stuff. We're just gonna stick it. Ah, we're gonna stick it. Put it there. Whatever. Um, Helmholtz free energy F equals U minus TS. Oh my god, I'm a little OCD. Trying to get this perfect. Make it look nice. One of them is TS is F. U minus TS. U minus T times S. Okay. F is internal energy minus the energy lost due to entropy. Oh. Internal energy minus energy lost energy. Okay, due to entropy. This entropy, let me write more like this. Entropy, energy loss. Here we go. The entropy energy loss is TS, internal energy, free energy. Okay, now, what is the postulate of statistical mechanics? Oh dear God, dF pressure is dF over dV. So, along with, there's so many things we can do with this partition function. Along with this particular one here, we can also calculate, P. Pressure, 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 pressure P. Well, if we take dV, and this time we are keeping temperature constant. Uh, temperature constant. Alright, alright, alright. dV, temperature constant. Reasonable, reasonable. Something like that. Put this as one long equal sign. No big deal. No big deal. It's not very neat. It's good. Whatever. Oh, it's killing me. It's like shifted over towards here. Alright. Okay, well, what exactly is the postulate of the statistical mechanics? Postulate of statistical mechanics. Third law of thermodynamics. S is 0, T goes 0. Okay. Oh my god. Sum of the positions and momentums of n particles. And we're doing it in 3 dimensions. Okay. I guess. That's a little bit crazy. Microstates. E as everything being keeping mu constant gives you CO2. Well, postulate of statistical mechanics is there are 3 postulates. Equal I priority probabilities. It's in fact this one. Oh my god, this is the ergodic hypothesis. Wow, we're doing ergodic theory already. Ergodic theory. Here we go. Ergodic. Ergodic hypothesis. We're gonna call this the ergodic probability, just because I like that word. Postulate of large numbers, macroscopic equilibrium. Alright, this is the second one says that is this one that we were working on over here. This is in fact law number 2, this particular thing we're working on. So this is the macroscopic equilibrium. Postulate of large numbers. Macroscopic equilibrium. Weird words. And the postulate of maximum entropy. This is number 2. This one is number 1. And actually this is number 3 right here. This is max entropy. Max entropy. Law number 3. And it says use the postulate to compute the entropy. Okay. So we're just computing entropy. S. Hopefully it's just KB ln of microstates. I I think I think that is correct. Hold up, hold up, hold up, hold up, hold up, hold up. Z is omega? No, no, come on. Don't tell me Z is omega. No, no, no. Z and omega are not the same. Omega is the total number of microstates. And Z sums over all the microstates. Wait, alright. Um, 1 over, thought the average internal energy is supposed to be when you receive times from mm, another way to express it. They were trying to give me something divided by omega. Canonical ensemble? Microcanonical ensemble? What's the canonical ensemble? What the fuck is the okay, the microcanonical ensemble. Oh, come on. The fuck is the microcanonical ensemble and the canonical ensemble? What the hell are these things? The microcanonical ensemble, the system has a fixed energy. The system is isolated, no exchange with its surroundings. Only microstates. The system can be in any microstate as long as total energy equals E. Okay. Some more vocab. Let's just put it over here. So microcanonical means that it's an isolated system. Isolated system. Okay. Well, in the canonical ensemble, we have contact with a reservoir. Let's say reservoir contact. Yes. So, reservoir contact. Canonical ensemble. Temperature is held constant. So I guess here we have T is constant. Yeah, if we have the reservoir contact, we would have a constant temperature. Oh dear Jesus, there's so many different things we have to do actually. Okay, so the microcanonical starts off with fixed energy. So we have E is constant. E is constant. And here we have T is constant. And uh, here we can do is we can calculate U, the expectation value of this freaking thing we calculated over here. Hmm. Partition function Z. But for this one, E is constant, but we use only the omega, not z in this particular situation. And we can calculate entropy using that. S as a function of this thing. And over here we have to use the freaking as a function of f. This particular entropy right here. There we go. Okay, S, S, and yes. And now we know whether we want to calculate entropy using the microstate, if we're in a microscopic isolated system and keep E constant, or if we are in the canonical state over here, in which case, this makes more sense. Here we have weighted microstates, weighted uh, this thing. Whereas on this stuff, equal probability. Equality here, which microstate on weighted PR, I think, would be more of what we want to see. Weighted probability. And then this is equal with the probabilities. Right. Lots and lots of research. This is a two-state system. Um, so what? So it's a two-state system. I don't know. Hell, if I just put two there, it's not gonna manage. work. But it's an isolated system. You have to use what? What? Functional energy. Wait, what? Dude, what? What? Hmm, What? God. This is so complicated. I don't even know what is happening right now. Okay, there's this multiplication we have to do. How to go with microscopic properties you need in. So incredibly difficult. The number of microstates is equal to some v to the power of n. I have to write this crazy thing somewhere. Write this crazy thing somewhere. Ugh. Oh my god, so this is going to be equal to, it's going to be equal to n, choose n. And n on the top, that's like the max total n. And on the bottom, what's that, I guess, I don't know. It's kind of set up right here, which is quite equal to n with the down there, and then we have some nice explanation. This is it. Piecing it all together, piecing it together super slowly. That might not be correct. That. So if I'm flipping, is omega equals 2 power n. And flip. Okay. Well, this is correct. This is in fact correct. This is correct. This is correct. Okay, we calculated that using n divided by n minus n. So, what? Really, but I guess that combinatorics versus the total number of microstates. Hmm. Okay. What? This? Okay, okay, okay. Okay. This is so. Let's try to define this a little bit over here. This is the total number of microstates. Total number, total microstates. Let's go. Total number of states is just this. But if we want this n equal omega, Specific constraint. Okay, so it's like a subgroup. So it's a subgroup of the number. This is the total number of states, whereas this is you can have your total number and here, but choose how many n is basically the number of states with a particular constraint. Say, um, let's say for example, maybe n equals 3. That means freaking if n equals 3, then what we're really asking is we want to know the number of states that contain 3 heads. Number of states with 3 heads. Number of states with a particular constraint. Number of states with heads, for example. And then, uh, so we wouldn't call it omega. We might call it omega. Hmm? Or what? What do we call it? I mean, what do we usually call this thing? Binomial coefficient. That's this friggin' thing. All this. This is called the binomial coefficient. Okay, total number of states. And then here we just put a sub n or something to indicate that it's really a subgroup of these omegas. And yeah, I think it's something kind of like that. This is called multiplicity. 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 That is this. Multiplicity. Okay. Let's move this maybe over here. Move this a little. And essentially cover all this. We got this. Hmm. Okay. We have this. Hmm. Okay. So like entropy. Okay, this was really weird. F is equal to negative kBT ln Z, and S is equal to kB ln. Oh my god. You want entropy as a function of energy? I wonder even counts the number of microstates of energy. What? So this is that omega 2. Oh, God. How the heck do I calculate omega? omega E, this thing. What on earth are we doing here? This whole thing is like so weird. Just there's not any information. Though. Number of cells you want. Your roundabout topic. How did we get e to the power n u to the 3n over 2? Where the heck does that even come from? Volume contribution. Oh, well, this now makes a little bit more sense. Every so often we encounter these moments of clarity because if we're in the microcanonical state, let's let's take a look. Uh, where can I put this? Mm, So for an ideal gas, if we want to calculate the number of microstates, we didn't want to multiply the different numbers of internal energies. We don't want the volume possibility options, the internal energy possibility options, and that's the number of particles. Um, Ideal gas with n particles. Okay, so the volume has n states. Each particle can be located anywhere in the volume. If there are n particles, then we take volume raised to n power. That doesn't really make too much sense. That doesn't really make that much sense, but let's maybe pretend that this is like a dV, so that every differential volume is paired with the particle. Wait, so for v to the power of n, every differential volume bit is associated with one particle? What? Spatial configurations. The reason Dn is each particle could independently occupy any position within the total volume. The number of spatial configurations. Okay, yeah. Okay, this kind of makes sense actually. Because V, let's span that. Let's give that some numbers from 0 to 9. That means we have 10. And that's for one particle. One particle can fit in each one of those 10 slots. If we have two particles now, each particle, it's just, well, there's just more combinations now. So, I guess that's what's going on here. Same type of stuff. Let's go look over here. We have, well, here's more like each flip gives you an N. Okay, so we're basically taking a little differential here with little particles. You can think of this as little dV, and in each little differential V, you could stick another particle. So that's why you have to go dV times dV times dV times dV, and so you're gonna get a zillion V's depending on how many particles you have. Okay, so I could sort of say dV corresponds to one particle. Therefore, dV dV, that just equals two particles. I'm just gonna put them. So every dV gets one particle. Every dV gets one particle. You can't put two particles in the same dV, right? But they can. It depends whether particles are distinguishable or indistinguishable. That's right, the Pauli exclusion principle. This is so funny. No way. Every little detail is so important. Every dV fits one particle if it's indistinguishable. So depending on whether we're doing bosons or fermions for the particles. Okay, well, so equals one fermion. I'm just gonna say one fermion. And this is Pauli exclusion principle here at play, by the way. Pauli exclusion. Oh my god, how cool is that? Okay, and then we'll leave it at that. I'm not going to go too much further into that. I don't really care too much about the other situations. But that's kind of interesting. That's how we get v to the power of n. Now, same type of thing for the next component, which is u. Apparently this is to the power of 3 halves. And, well, why is u to the power of 3 and over 2? Oh, don't tell me it's because of the 3 dimensions and because of 1/2. In fact, I guess it is. Holy shit. Okay. Yes, yes, yes. So, wow, let's do something like this. We're probably gonna have to move over here. Alright, there's so much more we gotta freaking cover. It's almost midnight. Uh, but this is all so important. We're making such slow progress. But now we have to put u here, and we gotta call it 3 over 2, 3n over 2. And we have to ask ourselves why. Because I don't just take shit. I don't just take shit for granted. I'm gonna figure out why. Well, kinetic energy is 1/2 mv squared, yeah? Um, well, let's just call it momentum. So let's put a proportion sign here. Dot, and this is proportional to the momentum squared. And we want to calculate px d dx, really. I mean, it's px, py, and pz. So, minus over 2. This is kinetic energy is proportional to this. There actually is that. Assuming there's no potential energy, and dy and a dz here. We take this in 3 dimensions. We in fact get 3 over 2. 3 dimensions. 3 degrees of freedom. Dimensions. Okay. Um, yeah, u to 3 and over 2. Trying to see how I might be able to write this in a way that makes more sense, because the only way you can really get this is if you did like u to the 1 over 2. What? Degrees of freedom. Summing over the square of the momentum, and each particle is 3. I still can't see why it's 3n over 2 in the exponent. This makes no sense. Well, this might make sense. This might make sense. Let me actually write P. What we're going to do is we're going to create a volume space with momentums. So volume of space with momentums, px, py, pz. We multiply these three together, py and pz, and well, that just equals p to the third. Oh, p to the third power. And now we have a 3 in the exponent. Let's remember that when we have n particles, we can raise this to the power of n. So essentially we have two types of freedoms, and they're kind of multiplying by each other. Think. Since there are n particles, we just put, since there are n particles, we just do either third to the third, or to the n, and that becomes 3n? Not quite. Hmm, I see. Let's not forget that, let's just consider this energy, this kinetic energy, it's really kinetic energy, whatever. If we want to do this, what we have to do in order to get P again is that we actually have to take the square root. So let me put 2m over here. And so let's just do that. Put that in the square root, realize that's what P is. So if we want to put P in here, um, now we get this idea. Where's the mu sum? Over here. So that's this thing without the pi. Um, Total energy is the sum of the kinetic energies of all the particles. I mean, that would make sense. U equals the sum of all the different energy states going up to n. This is kinetic energy right here. These two things are exactly the same because EI equals KE. If there is no potential energy. Okay, perfect. So we have the sum of these energies. U equals that, and this equals, well, now we have to put it all back in there. So now we have to P squared over 2M. Squared over 2M. And then also still take that sum there. I see, I see. This is for an ideal gas. Ideal. Ideal gas. You could do this for an ideal gas. Cut out that potential energy. Just call it kinetic energy. Oh my god, how do we go from here and get a power of 3n over 2? I see, it's like really complicated. You do like some crazy spherical stuff. Alright. Yeah, I mean, I can kind of see how, like, if you try putting this in there, you might have to, like, take the square root or something. This is very, very complicated, but this just simplifies to this. Again, this is for an ideal gas. Um, and then the final little piece of this freaking equation is, I think forces or something. Yeah, F. Hmm, I don't know if we need to deal with F. Do we need to deal with F? We do need to deal with F. That's what we deal with F. First, put green F over here. Green F. And this green F is trying to represent whatever other crap we have to deal with, like maths. And, and F. There's other stuff. There's other stuff. Well, that's great, but it doesn't really help all that much, man. Like, mm, so what? So what if we can do this? So what? I still can't calculate the entropy. Honestly, this entropy thing, I think I'm just gonna have to. Do I put in V to the power of n u to the 3n over 2? But what about F? There's like all this other F we have to do. This isn't even this isn't even ideal gas. This is some system just in contact with a heat reservoir. Thermodynamic differential relation makes this Yo, this is so complicated. I'm just gonna say that there's states. I'm gonna give up on this one a little bit because I just can't finish this. No idea. Alright, let's go to the last little piece. Thermodynamic differential relation. Energy turns of the system's temperature. Energy in terms of temperature? Mm, mm, didn't we already calculate energy? What? There's just too many types of friggin' energy, so I don't know what energy we want. We calculate the average. Well, I, I don't know what to say. This is so hard. Like, it makes no sense. Anyway, okay, so let's just kind of recap and see if there's any last little bits that I might have missed. I think I've got pretty much everything that I could figure out today. It's freaking 12 a.m. already. So we're kind of doing this crazy statistical stuff. Got like heads and tails over here. And so we have two possible states, and we're flipping them n number of times, and we can choose n. Say we have three heads, and we can make a little thing out of it. We have all this over here, Pauli exclusion principle with this. This is for ideal gases. I don't know what we're gonna do with this F over here. Um, we've got the three postulates, thermodynamics, Z partition function, and all this good stuff we could derive from it. I think that we are pretty much done with this for now. Alright, well, maybe next time we can do some more, we can do a little bit better. I don't know about this. This was really, really hard stuff. I didn't really understand too much of this. Trying to go super, super slow. Anyway, y'all, that was crazy. Peace.